presenter, Mr. Lindon Falconer. I'll tell you a little bit about Lindon this morning, colleagues. Lindon Falconer received his BSc First Class Honors in Electronics and Computer Science from the UE in 1997, and he has a MSc with distinction in Digital Technology from the UE also, which he completed in 2005. He's currently researching for a PhD in Electronics and Computer Systems Engineer in the Faculty of Engineering here at Mona. He received a Commonwealth Scholarship in 2014 to conduct joint PhD research with the Computer Science Department at the University of Sheffield in the UK. Lindon has over 20 years of experience working in the industry and more than 8 years in academia. He worked with Digicel for more than 11 years, where he specialized in value-added messaging services. And throughout the years at Digicel, he was promoted from engineer to senior engineer and then to engineering manager. He has over 10 years of working experience designing and building customized electronic solutions and has remote monitoring and control products in the market. He's founder and CEO of Falconer Limited. His area of specialization includes mobile communications, embedded systems, applications, speech recognition, machine learning, and the Internet of Things. Lindon is a senior member of the Institute of Electrical and Electronics Engineers and a member of the Acoustical Society of America. He's currently employed as an engineer and adjunct lecturer in the Faculty of Engineering and lectures in the Department of Physics also. What is missing, colleagues, from this introduction are some very important things. This is information I shared with you, is information that Lindon provided. But most importantly, we've got to tell you, he's a father and he takes that role very, very seriously. And the other very important thing I've got to tell you is that he's a past student of the Morant Bay High School, where he was my senior. And so Prof. Rees, when I had to call on him to fill in very short notice because our speaker had been delayed, you know, it was a time to connect. And so I give to you, ladies and gentlemen, Mr. Lindon Falconer, who is going to speak to us about modeling the effects of hearing aid algorithms. Over to you, Mr. Falconer.
Thank you very much, Maradine, for that introduction. And I really thank you for contacting me. You know, when you called me, I had something planned, but this is an opportunity for me to share with the University of the West Indies community, especially chemistry, because chemistry is one of those subjects that I really love. It was my favorite when I was going to Morant Bay High School. I was a top chemistry student at the time. So when you call, I'm really happy to be here and to share with you some of the work that I have done. I presented the same work at the IEEE SoutheastCon conference last week, Thursday. And so here, when you call me, I already have a presentation prepared. So I said, okay, it's no problem to present it. So I made some small adjustments, but for most part, it's the same presentation that was done. But the time at the conference was shorter than what you told me. So I added some more slides just to expound on what I've done. Thank you again. So today I want to share with you part of my PhD research. And in that research, I did 4 experiments, and this is one of the experiments. We're looking at modeling the effects of hearing aid algorithms on speech and speaker intelligibility as perceived by listeners with simulated sensorineural hearing impairment. Okay, so the structure of my presentation is as follows. I will explain the research problem and talk a bit about hearing aid fitting and performance issues. Then I will explain the computational representation of the speech signal after processing by the human auditory peripheral system. Then I will show how I represented hearing impairment computationally. Then I introduce my novel computational model and look at some experiments and results, then discuss the results and show some references and acknowledgement.
Sorry, Lyndon. I'm going to ask everybody. I'm unable, somehow my controls aren't working here and I'm trying to contact Terry, but there are some people who have their microphones open. In the meantime, I try to control this. Could you fix that for me, please? That's Ronique and some others. Thank you.
Yeah. Okay. All right, thank you. So the research problem, disabling hearing impairment is a problem throughout the world. Disabling hearing impairment has been projected to increase considerably, and the World Health Organization has predicted that there were 42 million persons with disabling hearing impairment in 1985. The number increased gradually up to about 360 million in 2011 and is expected to reach 630 million by 2030. Disabling hearing impairment causes a lot of problems. It prevents the person from communicating normally, especially in noisy environments. It can cause sadness and depression. It is known to cause dementia. It causes worry, anxiety. It can prevent the person from going to school, from gaining a job. So in effect, it has an health and economic problem which we need to address. Disabling hearing impairment is typically classified as conductive or sensorineural or a mixture of both. For conductive hearing impairment, this can be remedied through surgery or through wearing an hearing aid algorithm. So the conductive hearing impairment, the person with this type of hearing impairment can return to almost normal using surgery or a amplifying hearing aid. However, on the other hand, sensorineural hearing impairment is permanent, and this is the one we focus on for the research. Typically, the hearing aid is used to assist persons with sensorineural hearing impairment. The hearing is returned to a level that the person can perceive sound, but it depends on the severity of the hearing loss that the person has, or it will help that person. Many persons wearing hearing aids have complained about their performances in noisy environments. And this is a major problem. It prevents the person from participating in events, and the aim of developing these devices to assist persons to hear properly is to return them to normal functioning. But because of this situation with the hearing aid algorithms that are produced today, they're not as effective as would like them to be, so persons continue to complain. So although I must state that the algorithms have improved considerably throughout the years, but there are still some weaknesses. Also, there is a fitting problem with hearing aids. It typically takes a couple of days or even weeks for a person to adjust to the new signal produced by the hearing aid. So when someone goes to the audiologist to fit a hearing aid, it will take some time to listen to the speech signal, to adjust to that new sound so they know that they're comfortable wearing the hearing aid. So we have some problem in terms of developing the hearing aid algorithms and also fitting the hearing aid. So when we looked in the literature, we saw that there are a number of issues related to developing new hearing aid algorithms. Because the key thing is, if we can develop new hearing aid algorithms at a faster pace and improve their performance, then of course we can satisfy hearing aid wearers. Some of the challenges we identified were the time and expense to recruit hearing impaired individuals. And also the hearing impairment varies between individuals. So when you want to set up an experiment, it would be good to get persons with similar type of hearing impairment to conduct listening tests so you can validate the algorithms. And also it takes a long time for the person to adjust to the new speech sound. So to evaluate the algorithm, you have to wait days or weeks to know how effective the algorithms are. Also, as I mentioned before, the fitting problem. It takes a while for a person to adjust to the hearing aid themselves, and that is a problem, the time problem in fitting hearing aid and in developing hearing aid algorithms. So a possible solution that we looked on is in the early stages of testing the hearing aid algorithm and fitting hearing aid, if we can replace the listener, that's the hearing impaired listener, that is listening to the speech sound to see, you know, if the clarity of the sound, to understand the sound well, we replace that listener with a computational model. And this model is what I developed in my research. So this computational model is configured with the audiogram. So the audiogram represents the level of hearing impairment of the individual. So we configure the computational model with the audiogram that was measured from the particular listener. And then this computational model will mimic the intelligibility or the perception of speech and speaker intelligibility for a particular listener. So with this model, we hope that if it can perform well or perform similar to the user, then it can be used in the early stages of testing hearing aid algorithms and fitting hearing aids, so that we can reduce the time, the development time of the hearing aid algorithms and the fitting time of hearing aids. So the methodology used in the research, we decided to develop a physiologically inspired computational model. There are different models that have been developed throughout the years, but we decided to use a physiologically inspired model, a model that is based on how human perceive sounds. So I'm going to explain the different steps we have gone through in implementing this model. We also use a machine learning system to represent the knowledge of the hearing impaired speech, because we want to try and mimic the human as closely as possible. So before getting into that, let us look at speech and hearing. When someone speaks, the speech or the thought to be that the person wants to convey is first generated in the brain. And then the brain triggers the motor nerve, which triggers the vocal cords and the movement of the articulators in the auditory system or in the acoustic system. And then the speech sound is produced. The speech sound, of course, is a vibrating wave that is sent through the air, and it bounces off different objects and so on before reaching the listener ear. The speech sound is processed by the outer, middle, and inner ear of the listener, and then it is sent through neural impulses to the brain of the listener, and then the listener can decipher the sound. And if the listener understands the language, they can now interpret what was said. However, because of hearing impairment within the listener, or some listener may have a hearing impairment, that is where the problem occurs in the person identifying the speech sound accurately. So in representing the speech signal computationally, we use what is called an spectrogram. So the spectrogram is shown here. So here at the lower diagram, we show the speech signal it's showing the amplitude against time. So if someone say the word place, right? And this is the speech signal representing place, and this is a spectrogram. And the spectrogram not only shows the variation of the speech signal with time, it shows the variation of the frequency of the speech signal with time, and also the amplitude. So the darker shaded area shows the amplitude of the speech signal. And I can go further to explain that the speech signal or the speech or a word is broken down into different speech sounds. And in my research, we look on the IPA, International Phonetic Alphabet, where we look on the different speech sound within words, right? And so I did some linguistic study of linguistics to understand how speech sound is produced. And throughout the years, researchers have used different methodology to represent and identify different speech sounds so we can use them in machine learning systems. So to go further, in understanding how the human auditory peripheral system processes sounds, we look into the physiology of hearing. And I'm not going to go into the full details, but basically when the sound comes into the auditory canal and it enters the tympanic membrane, that's the eardrum vibrates and it moves those small bones in the middle ear, which vibrates the oval window on the cochlea, and then this trigger a mechanical vibration in the fluid in the inner ear. And this vibration, and this is interesting because this is the part that we use to represent the signal computationally. We looked on the vibration of the cochlea along the what is called the basilar membrane, and researchers have shown that the amplitude of vibration varies along the length of the basilar membrane, and the vibration depends on the frequency of the sound. So we took that into consideration, and this was work done by Brown and Cook in 2004, where they developed a rate 32 feature, which is a feature extraction methodology to mimic frequency analysis in the cochlea. And in this approach, what they did was to sample the speech signal at about 25 kilobits per second. They run it through a bank of bandpass filter, which mimics the filtering on the basilar membrane within the cochlea. And it went through some processes. Not going to go through the detail, but some signal processing stages are used to extract the speech signals. And this rate 32 speech features, or the features, are used to train the machine learning algorithm. So here I show on the right, I have the utterance here, which says, place green at Y1 soon. And this is the International Phonetic Alphabet that represents the speech signal, or the speech sounds, I should say, within the utterances, or each word. Here we have the variation of the speech signal with the amplitude against time. And this diagram here, the spectrogram of the speech signal, represents the variation of the speech signal in frequency against time, and also the amplitude against time. I need to point out that there in the shape of the spectrogram here, where you're seeing the darker area, this represents higher energy within the speech signal. So at the lower end is the vibration of the glottal pulses. Vibration here, you can see the frequency, well, it's not that clear, but the vibration is taking place here. And then we have formants, right? We have formants of the speech sound, and these formants are resonant frequencies. So you'd have known about resonance from, well, it's in chemistry and physics, resonating sound taking place at different frequency, and we have different harmonics. We have different high frequency sound, such as the fricatives, place this sound. You can see this high frequency sound here. We have some of the high frequency sound here, then soon, and the vowels of the formants, the harmonics feature of sound represented here. So these are some of the key features which we want to retain. So in the lower figure, we have the spectrogram now of the rate map, and these are the rate 32 features. This rate 32 feature, this is what we use to train the machine learning algorithm. And as you can see, to some extent, it kind of retains information, critical information about the speech signal itself. Because we couldn't use the spectrogram to train the speech signal because there are a lot of artifacts associated, a lot of noise associated with the signal. So extracting the rate 32 feature gives us a better representation of the speech sound that we want to identify. So in the experiment, we also looked on two different types of hearing impairment. Because we're going to model hearing impairment in normal hearing listeners, we looked at two different types of hearing impairment. We looked on moderately sloping high frequency hearing loss, and this is the audiogram representing that type of hearing loss. The audiogram basically shows the intensity, or the level, the hearing level of the speech signal where the person perceives sound, right? So it represents, so the person, this is representing the hearing loss at different frequencies. So a normal person would have a relatively flat graph. This person has a mild hearing loss. This one was called HI1. HI2 is represented here, where this is a more severe hearing loss. We call this HI2, and this is the spectrogram showing the hearing loss or the hearing deficit at different frequencies. So the frequency increases, then the hearing loss also increase. And this is typical for older person getting older, person with sensorineural hearing impairment. So in terms of simulating the hearing loss, because this hearing loss was simulated in the model and also in listeners with normal hearing, we use two different methods to simulate the hearing loss. A typical method that is used in simulating hearing loss is to add spectrally shaped white noise. So you kind of shape the white noise and add it to the speech signal to simulate hearing impairment. So we use a method by Deslodge and others. We use the same method they use to simulate the hearing loss, and additive threshold noise is used for threshold loss less than 60 dB. And this is what we use for the HI1 hearing impairment, the first hearing audiogram that I showed. For hearing loss with threshold greater than 60 dB, we use a different method called a multiband expansion method. So these are signal processing techniques. And with the first one, what is used, the audiogram is used to shape the filter, a noise filter, which this filter processes white noise, and it uses some critical ratio values which are related to how human perceive sound. And then this spectrally shaped noise is added to the speech signal, and then you have a simulated hearing impaired speech signal. The method here, I'm not going to go into the full detail, but this second method, the multiband expansion, it involves processing the speech signal through multiple, like 13 bands of fourth order gamma tone filters. And a similar method is used to add the spectrally shaped noise to that signal. So we have simulated hearing impaired signal. These methods have been shown to work by simulating hearing loss in normal hearing persons, and work was done to compare their performance with persons with real hearing impairment. And similar results were obtained for intelligibility tests. Well, intelligibility test is person listening to speech and identifying specific keywords. So here I have the rate maps. Here I have the spectrogram and rate maps for the speech utterance. The utterance place green at Y1 soon. So let me explain quickly. This here in the top row, we have the clean signal. The clean speech signal is the spectrogram of the clean speech signal. This is the spectrogram of the speech signal now processed with the hearing impairment simulator using HI1. And this is the spectrogram for it processed with the hearing impairment simulator using HI2. That's the different types of audiograms. Below, we have the similar representation for the rate map. And why I show the rate map, because this is what we use to train the machine learning algorithms. And I have some example here for you to hear. I don't know if you will be able to hear it, but I have the clean utterance here. And let me play it to see. Can you hear that?
I'm not hearing on my side, Lindon. Anybody else hearing?
Okay.
Yeah, a little bit coming through now.
All right, so I'll just play it quickly. All right, so what I want to demonstrate is the sound of the impaired speech. So the noise is added to raise the threshold of hearing, and then this is HI2. So this is what the listeners listen to in the listening booth. Okay, that's just to demonstrate the speech sound. So how did we represent the hearing impairment computationally? Well, we did so by mimicking how human perceive sound in a crude way, of course. And this representation here shows the clean speech signal is sent through an hearing impairment simulator, which is configured with the audiogram of the listener that we want to simulate. And then the features are extracted, rate 32 features, and then these features are used to train HMM, GMM models. And then this model represents the knowledge of speech. So in a crude way, this is how the human brain learns speech. And because the person has an impaired auditory system, they will learn impaired speech, right? So they will represent, when a new signal comes in, they will match it against the impaired speech. So we looked at two different hearing aid algorithms. We want to evaluate the performance of the system in evaluating two different hearing aid algorithms. We use one that is called a null RP hearing aid algorithm, which is popularly used. It amplifies the speech signal at different frequency band to improve the intelligibility of speech. And we also use another one, which is called a spectral envelope decimation. What it does is lower the high frequency speech signals so the listener can hear. I'll use some diagram to show you that. So here we have the clean speech, the spectrogram of it. Remember, the darker the area, the higher the sound. So this is the frequency on the y-axis, the time of the signal. So when it is passed through the null RP algorithm, you can see the amplification here. And this was done with an audiogram having these values. Here we represent the spectral envelope decimated algorithm. This one is very important. It's using a lot of modern hearing aid algorithms because a lot of persons with sensorineural hearing loss, especially persons 65 years and older, they find that those persons typically have age-related hearing loss. They will tend to lose the effectiveness of hearing or perceiving high-frequency sounds. So the idea here is to move the high-frequency sound into area or into a frequency band where they can perceive sound. So it does have compression of the speech signal. As you can see here, this speech signal here, this high-frequency sound is compressed, it's compressed and shifted down into the frequency band. So of course the user, they need time to adjust to the speech signal. So if we can use the machine learning algorithm to show that the intelligibility or the clarity of speech is improved, then it can demonstrate that the human may benefit from it. So that's the idea. So here I introduce a novel computational model. The novel computational model is highlighted in dotted line here, the dotted red line. And at the heart of the novel computational model is, yes, at the heart of the computational model is a missing data automatic speech recognition system. This system here is designed to mimic how humans perceive sound in noise. So if you're listening to sound, speech, or any other sound, and there are noise in the background, what you'll find is there are particular areas, if you look on the spectrum of a speech sound, where the noise obliterates the speech sound. The noise energy is higher than the speech sound. And there are also parts of the spectrogram where the speech is higher than the noise. So that's how humans tend to listen to speech in noise, and you may miss certain things, but you pick up another part, and your brain can help to filter out what was said. You can basically assume what was said. That's why sometimes you make an assumption and you're wrong because you only heard parts of the speech sound. So this missing data automatic speech recognition system does that. I'm not going to go through the details of its operation, but it uses information from the clean speech. It uses knowledge of the clean speech, and it also uses hearing impairment simulator, which are configured with the audiogram of the listener that we want to mimic. So that's the important thing. We're using the audiogram of a specific listener to mimic that person hearing impairment. And it also uses the machine learning models, which are trained on clean speech, which was passed through the hearing impairment simulator. And this model basically generates intelligibility scores. I'm going to explain the intelligibility score in the next slide. The model also can tweak the SNR threshold to identify areas where the speech signal is usable, and you can increase the size of the different areas in the spectrogram. So the experiments were conducted using the listeners and using the model. So in this diagram, it depicts the listener with a listener with normal hearing. And this listener, we listen to speech sound. So we have a clean speech signal. It was passed through or added to that speech signal was speech-shaped noise. This speech-shaped noise mimic a noisy background, right? And then it passed through the hearing aid algorithm. The aim of the algorithm now is to improve the intelligibility, the clarity of the speech. And the hearing impairment simulator now is configured with the audiogram of the hearing impairment that we want to mimic. And then the normal hearing listener listen to these speech signals or the utterances, and then the person would identify, they would press on the keyboard and identify the letters and digits that they heard in the speech signal. So we use two types of hearing impaired, two audiograms. And in the experiment, we use 20 normal hearing listeners with simulated hearing impairment. The same thing was done for the computational model. The computational model is shown here, and I explained it before, and its task is also to identify the letters and digits in the utterances. The algorithms that were used, the hearing aid algorithms, were the null RP algorithm, as I explained before, that amplifies the speech signal, and we use the null RP mixed with the SED algorithm to basically gives a better performance. You want to improve the intelligibility and also lower the speech. As a baseline, we also use a no processing algorithm, we call it, where no processing was done on the speech signal. It was just passed through to the listener. So it was used as a baseline. So in terms of analyzing the results, what we did in this work was to use listeners' performance or human performance and then compare with the model to see how well the model matched listeners' performance. This is a method that is used in a number of studies similar to this one. So first, we looked on average keyword intelligibility score using different hearing aid algorithms. So I showed the diagrams here. The diagram in the top row shows the result for the model, right? So we have the diagram in the bottom row shows the result for the listeners. And in the left column, we have the result for HI1 hearing impairment. In the right column, HI2 hearing impairment. So let us look on one of the figure. This is the performance or the percentage correct. So when the model identify keywords that were digits and letters in the utterance, this is you calculate the percentage correct that was received, that was achieved. And this is using no processing, no algorithm was used. So for digits or for letters, this was the result, and this was the result for digits. And this was using a null RP hearing aid algorithm. And as you can see, the intelligibility score has increased, has improved in comparison to no algorithm. The results here show the result for null RP and the spectral envelope decimation algorithm. And the result was almost similar to the result for null RP alone. And it shows that for sure the digits are more intelligible, are clearer than letters. And that's known. And the results for the hearing impairment 2, the HI2, it shows similar trend in terms of hearing aid algorithm, but you can also see that the intelligibility score is less than for HI1. And this is so because HI2 is a more severe hearing impairment. So this is the result for letters and the result for digits. So this at the top is for the model. So let's look on the result for listeners. So the results for listeners were average across listeners, and we have the same algorithm here, null RP said. You can see the trend for the listener follows that of the model, or I should say the model follows that of the listener. And the result for digits, of course, more intelligible than letters. And this is the result for HI1 and HI2. To determine how well the model performed in comparison to the listener, we did a Pearson correlation of the results. And the results using digits for the model versus listener, when using HI1 hearing impairment, we got a correlation coefficient close to 1 with a p-value of 0.02 shown here, which was less than 0.05, so we said that result was statistically significant. The same was obtained for HI2. We also looked on the performance with letters, and we got similar results that were statistically significant. So these are the results for average keyword intelligibility. We also looked on the ability of the model to predict the intelligibility of digits, because we want to see how well the algorithm can improve the clarity of digits within the utterances. So we have in this diagram, it shows the result for HI1 on the left, result for HI2 on the right, and the listener's results are in the the bars that are not unshaded bars, and the model results shaded bars. And you can see the digits here, 2, 3, 8, and so on. These are the digits that was recognized, and the results in the top row is for no algorithm. In the second row is for null RP. The bottom row, null RP SED. Right, and the correlation coefficient and p-values are shown at the top here. For this result, we didn't receive any value that was statistically significant, or none of them were statistically significant. But in some sense, you could see the model tracks the listener to some extent based on the p-value obtained, especially using null RP and HI2 for this value here. We also look on the performance in predicting letters intelligibility. And the graphs are organized as shown, similar to the digits. And we got some statistical significant results for null RP algorithm using HI1 here in impairment simulation, and also for the null RP SED algorithm using HI1 hearing impairment. HI2 didn't receive any statistical significant values. We also looked on how the model predicts the intelligibility of speakers, because this is important. It is known that different speakers speak clearer than other speakers, and so they are easier to perceive in noisy environments. And especially it is known that female speakers tend to have more clarity, or sound clearer, or more intelligible in noisy backgrounds, because of course of the frequency, the higher pitch in which they speak, which tend to better represent the signal in a noisy environment. So the diagram here shows the result for male speakers on the left here, result for female speakers on the right. And this is the result for the no processing at the top row, middle row, result for null RP algorithm, the bottom row result for null RP SED algorithm. And the results that were statistically significant were for the female speaker using no algorithm, and for male and female speaker using null RP, and for female speaker alone using null RP SED algorithms. So based on the result that was obtained, we saw that we got statistically significant values for some of the results. But we also know that for average keyword intelligibility, that's where we got a better match between listeners and model. And one of the things to note there is that when we did the average calculation, we averaged all the results for all listeners across specific hearing aid algorithm, the result from the experiment, it showed that we had some data sparsity, I would call it, or we needed more data when we started to look on individual intelligibility score. We started to look on letters, individual speakers, digits. We had less data. So coming from that, we're thinking that the result could have been better if we had more data. However, there were a number of constraints in conducting the experiment. The listeners were only given 1 hour to sit in the listening booth to conduct the listening tests, because after that, the listeners started to get fatigued and it's difficult to keep them longer. So that was a drawback. Which means that if we're going to keep them longer, we may have to run the study over a longer time to get more data. So the results show that the model has some good results. So some aspect of it can be used, it's promising, right? And in terms of improving the model, we think that we can replace the GMM HMM machine learning model to use a more, I would say, sophisticated model that is better in representing the speech signal. It is known that deep neural networks such as using HMM and DNN perform better than GMM, HMM models. Because when I started this work, GMM, HMM models were the state-of-the-art model at the time, more developed and recognized, has been around for a number of years and performing well. But DNN, HNN model, they have shown to be better at representing the speech signal in noisy environment. So going further, I think it's best to now replace that part of the computational model, either using DNN HMM or using a recurrent neural network, which we hope will, represent the speech better and better match human results. And of course, another work, which we already did, is to use listeners with real sensorineural hearing impairment instead of using listeners with simulated sensorineural hearing impairment. So I would like to thank and acknowledge my primary supervisor, Dr. Andre Coy from the Department of Physics. He's the one who guided me through this work. And I would like to thank Professor John Barker from the University of Sheffield, who guided me when I was there conducting the work. And Dr. Paul Aiken, my research advisor, I would like to thank him also, and especially the University of the West Indies, the University of Sheffield, and the Commonwealth Commission, who funded my research and ensure that this is possible. So here are some of my references. And I would like to thank you. This is my presentation.
Thank you very much, Mr. Falconer, for some exciting work that many of us just learned today is going on right here in our faculty. And we want to say special thank you also to Dr. Coy, your supervisor, who was also instrumental in suggesting and getting you to present for us here today. All right, everyone, so we are opening the floor. Lindon he hasn't got the PhD yet, he's wearing the hat, but he's got to do that he's got to do the final lap. So we need to have a robust discussion so that we can help him to prepare to defend this work. And so we're going to open the floor for comments, for questions, for suggestions. You can put your hand up, or you can just open your microphone and go right ahead, because I don't really see anybody rushing to say anything at the time. Is there anyone who would like to start? So Linda, okay, we've got Dr. Min, Zayar Min. Please go ahead, Zayar.
Hi, good morning. Everybody can hear me?
Yes, sir.
So just wanting to ask about the simulated hearing loss. You went with a noise background, right. Trying to hear keywords in a noisy background. Right. How would the simulated hearing impairment data compare if the sound wasn't necessarily in a noisy background, but the sound itself is muted, whether by using noise cancellation technology or to simulate the hearing impairment in that sense? Do you think? Yeah, I just wanted to hear your thoughts on that.
Okay. Yes, a good question. We looked at that in terms of the reasons. So first, definitely we would have gotten better results if we did that, because one of the weakness, so you pointed that out, of the algorithm is representing the sound in noise. So yes, the results would have been better, but what we wanted to do was to mimic the real world, where typically the sound that you want to hear is normally there are some background sound. So that's why we added the background noise. So you're correct, it would have shown better results. But the aim was to try and mimic a real world situation where there's always noise accompanying the speech signal, especially when someone is maybe at a conference, at a bus stop, at a restaurant, a stadium, and so on.
Okay.
Okay, thank you. Sorry, can I have a follow-up?
Yes, you can. Yeah.
So I mean, a hearing aid technology nowadays is pretty advanced now with different, even in a hearing, in one hearing aid, you can have different programs and, you know, with smartphone, connecting it to smartphone and stuff. I wanted to know also, I guess in a follow-up way, if you can, if you're looking to, or if you can utilize these things to improve the hearing aid efficacy when it comes to an environment where there isn't as much noise, like for example, on when they're trying to use a telephone, or you know, in this day and age of Zoom meetings and stuff.
Yes.
If there's any suggestions or ideas or plans, I suppose, to go along those conditions.
Yes, yeah. Yeah, thanks for that again. So yes, you're correct. And based on the current technology and based on a different environment, there are different approaches that can be used. So the research group, the SPANDH group, Speech and Hearing Group in Sheffield, they're doing exactly what you talk about. So definitely they looked on different environments. So as I said, quiet environments on the phone, in a teleconference room, and so on. So yes, work is being done in that area to improve on that. And actually, in an environment where the noise is low, hearing aid performs well. So that's typically not a major problem. So one of the things that we try to do with this approach here is to develop a model. So if we can develop a model, and with the current technology, the models will be placed in the cloud somewhere. And depending on where the hearing aid wearer is, if they're in a background that is not so noisy, then you change the model and use a different model. And then if they're in a noisy environment, you automatically replace it with a different model. If they're speaking to a specific speaker who is not speaking clearly as other speaker, the model can adjust to that speaker and so on. So that's the idea in terms of how we want to look at this particular research. What you mentioned is quite interesting. There are a lot of work going on in what you mentioned just a while ago. Noise canceling algorithms and stuff like that.
Thank you, Dr. Min, and thank you, Mr. Falconer. Before I go to Dr. Coy, I see your hand is up, Dr. Coy. Let me just throw one in here, Lindon. Is there a particular ratio or threshold value of pitch to intensity, pitch to amplitude? You know, there is frequency and there is amplitude, which affects pitch and, wait, let me go again. Frequency and amplitude affects pitch and intensity respectively, right? That's how it goes.
Right.
Right. Is there a particular ratio, a threshold value that allows these devices to work optimally?
It's an interesting question. So let me see if I understand fully. So you mentioned the intensity of the sound, and of course the pitch or the frequency. The pitch, depending on the pitch and the intensity. So you're saying if there's a threshold.
Yeah, because both things affect the clarity of the sound, and you mentioned about women versus men being clearer because of the pitch. But I'm sure there is also that balance between pitch and amplitude.
Yeah, man, you're correct. So so it is known there is a term, Lombard effect, right? Lombard effect. I was trying to remember that term, where when you're speaking. And this is intensity now. As the background noise gets higher, your speaker naturally tend to increase the intensity of their speech, the volume of their speech. So in terms of a device that automatically does that, so to some extent, there's some automatic gain control in hearing aid that will try to do that to increase the pitch. But in terms of, my work, I didn't look on that in particular. But to answer you in terms of the device, if there is a particular value, I'm not sure. I think so, but I'm not 100% sure to expound on it.
Yeah, it's just a thought.
Yeah.
I appreciate your comment on that. So we have Dr. Coy who has his hand up. Go ahead, please, Dr. Coy.
Good afternoon. Thank you, Marvin. Great presentation, Lindon.
Yeah, thanks.
As always. So I was just wondering about the use of the model in different jurisdictions, because it was developed with a particular database.
Right.
So in English speakers of British English, so to speak. Have you given any thoughts as to whether or not the same model, without any retraining on data from, say, Jamaica, would work for Jamaican listeners?
Yes. Okay. All right. Thanks for that question, Dr. Coy. So in answering that question, so the model, I bring the model here, and this represents the learned knowledge of the speech. So in the work it was trained on British speech from British speakers. So if we're going to use Jamaican speakers, I think if we have a corpus or a database with speech from Jamaican speakers, yes, we could retrain the algorithms on Jamaican speech from in Jamaican English, Patois, or any other language and it will work similarly to represent the speech, because this is the trained or learned knowledge of the speech from a particular language. So I expect it to work similarly on Jamaican language. The question fully?
Absolutely.
Yeah. So it should work well. Just to retrain it on the speech signals.
Okay, thank you, Dr. Coy. Is there any other question or comment from our audience?
Dr. Singh, there's a question in the chat.
Thank you, Prof. Would you go ahead and read it for me, Prof?
Rather than read it, let me reinterpret it. Well, the question is asked about, are there any implications for the outcome of your work utilizing existing technology infrastructure? And they say such as mobile phones and other ICT applications. I mean, and my take on that, because funnily enough, I was thinking the same thing. Often when we're on the phone, especially if we're having one of these WhatsApp calls or whatever it is, sometimes you can have real problems. So I'm not sure if the person, Pat Lewin, is asking exactly that question, but mine was more specific. Say about WhatsApp calls. Can your model help to cancel what we call noise in that, which might be even more random than say, sitting in a bar or a restaurant or a crowded place where a lot of people are talking?
Okay, yeah. Very good question. Thanks for that. Okay, so the model as designed now, as shown here, is just to identify or to predict the intelligibility of different keywords within the utterance. However, to answer your question in terms of improving the intelligibility of speech, now aspect of the model can be used to do that. So this missing data automatic speech recognition system, the model would have to be modified, of course, and then parts of it could be used to extract the speech signal and then to recreate the speech signal. So actually that's his work. That's an idea that Dr. Coy has, and which we think we're going to look down the road how to implement that. Because the idea is to pick the usable speech signal from the noisy background and then to recreate. So it would be a form of filtering, but it will be done in a way similar to how human perceive sound. And Dr. Coy takes a book, we call it a textbook, a book that was published on human perception of speech and mimicking that. So yes, in future work, we can use concept from this model to implement such a system, but this model has to be modified.
Right,
Wonderful.
so hopefully, I was just going to interrupt, sorry, Dr. Singh. So hopefully when you and Dr. Coy make your millions, you remember Pat Lewin and I.
Okay, we will.
Thank you, Prof. What is important too is to say that Pat has said this is really great work, Lindon, and Pat Lewin is from the National Commission on Science and Technology. What would be really great is that Pat remembers how great Lindon's work is, and the National Commission can put some more support into this kind of work and other types of work like this going on in the faculty. Pat, it would have been nice to hear your voice. The National Commission is certainly a friend of our department and a friend of our faculty, and it's great to have you and your colleagues here. All right, everybody, 12 o'clock is upon us. I don't see any more comments or questions. No, not in the chat, no hand up, and the time is up. So, you know, we have to congratulate Lindon on this kind of work. And so from wherever you are, I ask you to join with me in giving him a round of applause on this work. And especially also thanking him for responding so very quickly. You know, that's the kind of way you want to be comfortable in your PhD work, so that you're called last night and you can do a presentation this morning. Wonderful. Everybody, before you go, so thanks again, Lindon. Thanks again, Dr. Coy. And we do wish you all the best as you go forward with this work to make it impact people's lives. Yes. And serve the mission of science, that is to make people's lives better, right? Science for humanity is what we do here. Now, before you go, I'm going to ask you guys to, just for a moment, for a minute, observe that another of our colleagues in the Department of Chemistry has passed on, Mr. Trevor Amiki, who lectured in the department in the OSH program and also in the Applied Chem program, has passed on. And we want to acknowledge the contributions that Trevor himself has made to science, to this country, and certainly to our department and our faculty. So I ask you just for a minute of reflection on the life of Trevor Amiki, starting now. Thank you very much, everyone. And thank you for joining us again for another in our Thursday seminar series. I wish that we all keep safe, keep healthy, and come right back here again next week, Thursday at the same time. I see you. Have a good rest of the day.
Okay, thank you.